Right, so now recording. So that's really awkward. So what I'm just doing is just downloading the original model that I put together to actually build Bill and Ted. And I was just fascinated by the idea of learning and the idea of fundamental learning. Now, I know as a research thing, it's all already been done. But from my experience, I had no real experience in doing this. So I was fascinated with could we build machines to start building on that method of learning. So in this case, what I wanted to do was to have two machines that could learn from each other the way that we learn from each other, which is essentially we learn by example. So in a lack of better words, two of these should be able to pass data backwards and forwards. It sounds really nerdy. It is incredibly nerdy, but it was a fascinating subject. So this is here because this is a push rod. But the idea of this, oh, got another person visiting. There we go, nailed it. So the idea of this was particularly simple. Look at that, the eyes are a little bit out, it's awkward. So all I did is I designed the human head, human skull, if you will, and that was the pure housing for how this thing was going to function. Underneath this, as you can imagine, it's all motor driven. You've got the accelerometers, we've got the control box, I was actually using a Raspberry Pi, and then from there, a friend of mine is a dentist, and he sent me some human teeth, which sounds weird. So what I did is amalgamated the real human teeth into it. And it was just about really understanding how this would function. Now, predominantly, this design went a little bit poorly, and it actually had to be shelved because these eyes, under the learning technique, the way that these eyes move is they move too much for a sensitivity. So I've had to redesign, and I've realized that the size of this is gigantic. I actually made it 25% bigger. I actually made it 25% bigger than the human skull. So what it did is just made it that little bit bigger, and it just gave me lots of space to mess around with. So I have actually moved on from this, and there is a new design. Now, what am I actually telling you all this for? I'm just going to hide this. So I'll hide the skull. This was the neck plate. Right, I'm being hounded by yeah, I muted the mic, so don't panic. It's not that everything had gone poorly already. Right, so yes, back at it. Right, so yes, back at it. So the idea of this was to support the actual weight on it, and I wasn't sure about these servos in particular. Now, I've messed around with these servos. That's why the lining on this is all over the place. What I thought we would do is we could actually look at this servo in particular. Now, if I remember rightly, I don't remember very accurately on this. If I remember rightly, the weight on all this together was 2 kilos. Altogether with this, it was 2.5 kilos. So what we're going to do is we're going to select a servo, ideally, that can actually commit to this job. Now, I did predominantly use a servo, which is a HG 645 servo. Some comments are getting very interesting this morning. It's putting me off from being able to actually do this. But anyway, yes, sorry. So what we're going to do is I'm going to predominantly focus on this servo. So I'm going to save this. What I'm going to do is I'm going to save as, and we're going to build a package up. I'm going to upload it to Blackboard straight away. Then what we'll do is we'll bring it back down, and we'll call it servo test. And you'll notice this is the reason I've gone through the model is a lot of you are facing in the same conditions. So I've gone through the model. I'm just going to get the servo out, and I'm going to save this as a step file, put it into here, and then I'm going to save it. Right, so that's still not the end of the road. The other thing that we know is that there is a custom horn, and yes, they are called horns. I'm going to export this custom horn. So that's the custom horn. This actually was made of PLA. So I'm going to save again, save as. And what I'll do is go to desktop. I'm going to do the same again, put it out as a step file, put it onto servo, and then I've got the servo horn fixing. And then there is the actual servo horn, which sits underneath, which is your very stereotypical disc. So now what we want to do is save as, put that on the desktop. So we go servo, and then we're going to do the same again. And what this is going to do is just build me up that package. This in essence is a miniature version of what it is that we've been doing and what it is your assignment needs you to do. So that then allows me to just look, because when you look at it really, when you do really look at it, arguably I could turn these two into one piece, because the idea of these two being fixed, because that's what they are, you've got your screw points here and it'll be fixed directly to it. So what I'm going to do is go first, right click on here, and I'm going to turn it to 7-zip. I'll turn it into a zip file, and just going to nip onto Blackboard, and I'm going to upload it to Blackboard. Or in fact, what I could do is not going to upload to Blackboard. Not going to upload it to Blackboard. I'm going to go into Files, and I'll go into Class Material. You guys should be able to access this. This will be quite a useful test, because if we are going to do this, I need to know it's going to work. So I'm going to drag and drop that in. Right, so it's in there. You should now be able to open Teams and be able to grab hold of that, not a problem. If anybody has any problem, can you just give me a shout, and let me know? So far, so good. Yes, Corona, you look like you're doing all right as well. I have my guesses who Corona is, just saying. This is so weird, so weird. Anyway, right, so it's going to delete that out. Don't need that for now. So drag that out, and that is, so I think, touch wood, I think this method is going to work for us to be able to pass data backwards and forwards, which will be epic because of the issues of, well, you know what it's like, you email all this stuff, and when it comes to submitting the assignment, I'm thinking about doing away with bloody this file exchange crap that the university has, and just using this for you to drop on your assignment, because then there should not be an issue, and it's instantly there. Right, rant over. I'll go on to MATLAB. Now, as you're well aware, 2018, 2018A is, 2019A is the one that still has all the functions for both Surface and Solid. 2019B is the one that's got that issues with it. So I'm going to go with 2019A. I'm going to run it in. Give it 2 minutes, as ever. Give it lots of minutes. So, and when we're ready, what I'll do is I'm going to navigate to the folder, because I'm going to just start this procedure now, make sure it's good. So I'm going to go to Desktop, click Select, and then from the top level of the folder I'm using, I'm going to right-click, going to go to Add to Path, selected folders and subfolders. So we double-click in there, and now we know everything's accessible from that particular point. What I'll do is go New and Simulink Model. Again, as we're going through, if there is anything that you think, I don't know what's going on, I'm not sure what's going on, please, please stop me. Please just say something. I don't mind. It's just because this environment is very, very strange for me, as for us all. It's a little bit odd, so it's just, you know, it's just getting used to it. So 2 seconds. Right, let me just double check something, make sure I've got everything I need here. Okay, right, yeah, got it here. I've typically done a very simplified example for applicant days, and just figured we could use some of the notes. So what I want to do first is, I know that I'm going to need to set up an environment. This is about the servo testing, and I need to make sure that I'm going to be able to get a good servo that'll deliver what I want it to. So I'm first going to go to my Simulink library. What's the first thing that I need? Of course, it's the world. So I'm going to extend, go utilities. Some of this I will relatively go quite quick with because we have done it. The beauty is I am recording it. If something becomes a little bit unsure and you're not sure about what's going on, you can always come back. What I will do on Blackboard is I will keep uploading it as a simulation session with the date, and the model will be up there as well, just so you got a full reference to it. And each model that I'm going to do in these sessions will be based on one particular point of the assignments of that you're doing. So this one, for anybody that's unsure, this one, hi Nick, this this one would be predominantly aimed at the robot arm, because the robot arm, what I am asking you to do is to pull out the torques that are occurring and how these torques are happening. I'm definitely not answering that. So I'm going to drag and drop solver configuration. And then I'm going to go multi-body. Now, brilliant. So I've just realized that Nick's close by. I'm going to go on multi-body, and I'm going to bring in a mechanism configuration. Then what I'm going to do is I'm going to bring in frames and transforms, and I'm obviously going through a world. The world obviously gives me that that origin for reference for the beginning point, if you will, and spin that round as well. And then I have my world set configuration. What I think I might do with this is I'm going to revisit different things. So the one thing that I do actually like about this particular configuration is it's all about the pan and tilt of the actual head. So it's an interesting one, because we could essentially build this up in particular examples. So what I might do is we might look at this, and I will then jump to something more which is more in the piston idea. I'll go through that example again, because I do know it's left a few people feeling a little bit awkward in that one. So I do know that's awkward. I do know that's been a bit of a tricky one. Right. Just focusing on this servo. Now, the one thing that I know is I'm going to be operating around the axis of that servo. Now, the reason I was just stepping off a second ago is because this was the presentation slides. One second. Just flip this over. Now, come on. Right, here we go. Sorry about that. Just taking me a minute to get this damn thing to move. Right, so this was the particular slides that I've used before. So that is the project. I introduced it to the students as to what this thing was made from. So the internal structure was your aluminium, your RR58, which I know was quite expensive in comparison. Using the Hi-Tech HS645. Now, these are the particular motors that we're going to be looking at. It's got... Right, so this is what I'm interested in. So that's the servo output. That's what it can actually deliver on. I don't think I've actually have I put the weight in this? Yeah, the head of the whole thing weighs. So we're gonna 8.53 newtons of force is going to be acting on the servo. Now we need to be able to rotate that servo. So what we'll do provisionally is we'll assume that that is maximum force acting straight down. We want to see if it can do that. Now, there's a few things about the servo output that we need to be aware of. First thing I'm going to do is I'm going to go to body elements and I'm going to drag and drop a solid. Now, if you remember the file solid and the solid, the issue that I was having is that the file solid refers to an area based. So basically, it's a surface. The solid refers to volumetric. So it is a solid piece. And that's what was leaving me all over the place with this. It's a bit of a pain in the backside. Totally get that. But what I'm going to do is go with that solid because, interestingly, MATLAB still haven't answered me exactly what that initial problem is and where that problem's coming from. So, what is it, Nick? You do have a raise your hand function, so oh no. There's always one, is there not? I'm even tempted to put that comment on the record screen. I'm kidding. Right, so what I'm going to do is bring in my 645. It's going to be the main body I'm going to be operating around. So let's first bring it in. And what we'll do is go to File. I'm trying to also follow procedure, which I would expect, you know, typical things that I'd expect. Now, this is just so that this can be moved around, because I'm aware of you guys, some of you will be at home and you'll decide, you know, one second. Oh, it's because it's not been updated. Right, that's actually totally just died on me there, so let me just try that again. So come down, I'm going to go servo, step, sorry, and I'm going to go to that servo. We've got the servo, and click open, and then F5 that, and it'll bring in the body. So we know that's the body. That's a good shout. That's a good shout. I'm gonna have to just call you Corona. That's a good shout, Corona. Just because weird. Just because I'm using this as 2019A, but what I'll do is perhaps do it in both formats. So at least then we've got a reference to the two. So so what I'll do first is I will set this up as a file solid and then do it. And then what I'll do is I'll set it up in both remits. So what I should say as well is I'm going to call these session numbers. So coming soon will be emerging. It's just because we are in a really big freedom point here of where even if anybody's interested for Engineering Society, I do know that that we're all being restricted from the buildings. It's official lockdown as of today. Well, as of tomorrow morning. So there's no reason why we can't do some other stuff to support for Engineering Society and a little bit in this, if you will. So doing the stuff that I was promising, which is using microcontrollers and feeding it straight into MATLAB. No reason why we can't do that. Right, so I've just gone on a bit of a side note there just to give you an idea. Right, so according to the website, the weight of these servos are 60 grams. So the first thing that we're going to do is, this is technically a full assembly, as we all well know. So I'm going to drop this down and I'll set this to 60 grams. So I'll go 60. Oh, sorry, that's me on density. So I'm going to go drop it to grams and then I'm going to drop that and then I'm just going to put it in as 60. I'll update that. As I update it, as ever, updates my center of mass, my moments of inertia, and gives it so I can really operate this in a far better condition, as we know. Now, the one thing that I do know with this servo, it's a real pain in the ass as far as a few things. So I'm going to click on my frames. That is the initial point of frame position. So if I bring that down, for a reference, that is useless. I mean, really, it's just no good at all. So what we know for what we're trying to set up, 2 seconds. Oh. So what we're trying to do now is we're going to attach some frames. We're going to attach some frames, and we're going to first start on the initial point of rotation. So I'm going to go into frames, and I'm going to bring in my first point. So what I'll say is horn. So then from there, from there, what I'll do is I'll attach onto there. And now the issue is if I attach it onto there, what would be the big issue? Well, in fact, let's try and set 2 different ones up. Now, I think for me personally, if we're going to use that point there, it's not going to work out as well as I'd like it to, because as I bring in the servo horns, they're probably going to end up being wedged halfway down. And what I'd like them to be is actually to sit correctly. So first things first, I'll actually use the centroid. I'll use the center of the curve, and I'll just click save. And I'm going to leave R on for the minute. It's only a fixture point is R at this point. So what I'll do first is I'll bring that down. And now I'm just going to bring in the file solid, because as Corona said, we could do with really figuring out the both options. Just because I do appreciate that some of you will be on 2019B. I should point out, if you get home and you get so annoyed with 2019B and it's really, really frustrating, what I will do is, what you can do is you can install 2019A over the top of it. It's a weird setup. It's the first time I've ever really done it, but you can install 2019A straight over the setup. So it's up to you, but I will still do it in the Surface version as well, which is on here. So if I go to my 645, my MG servo, go like that. I'm going to repeat the same process again. This is just for completion, really, so everybody's aware. Just dropping address so that we can move around, so that we can move this around, and anybody who downloads this will work for as well. So I'm going to go F5, just update the model. Then I'm going to go to my I'm going to go to my custom mass, and we said it was going to be 60 grams. And these things really are 60 grams. I mean, I don't know who's into servos. I don't know who's well aware of them, but they are relatively light. They're not heavy things, but their output is, these torques are immense on this. So what I now need is I need to add a frame. Now, don't forget, this reference here is actually referring to centroids now. So I use that edge. Now, ironically, it's the right spot anyway, so I've got servo mount. I left the other one as F1, but it doesn't matter, but I'm going to go servo mount, use that selected area, and then I'm going to apply it. So I'm going to save it. I'm going to apply. Now, I won't lie, I've been trying to set both of these up, not quite right. just for some giggles. Now, the reason I say that is, so I'll call this, I'm actually going to, like I say, I'm going to upload this because I think it'll be very useful to have. So you can see it, so you can see the procedure that I'm going through to do it. So I'm going to repeat this thing again here. And well, obviously in this case now, it's no longer a solid, it is a surface. So we've now got two alternate options between the two, and they do commit to the same thing. So the real question is now, if I go back into my solid, I need to fix the other one as well. I should have fixed the other one, but if I go back into my solid, I go to my frames, and then I go to edit that horn. Right, this is what's been confusing a lot, been getting people really pissed off with it. There is a massive error there. Is anybody aware as to why that error is there? And or is it not why it's there? Because I put it there, obviously. Is anybody aware as to what the error is? Always think, always remember, your axes of anything always defaults to Z. Always defaults to Z. Now, to make my life easier, what I try to do is always, I try to keep everything relative to this datum. So I know it sounds crazy, but what I actually want is I would like things to still remain positive wherever I can. So what I actually want is I want Z to be in the Y component, but I want it to be facing upwards, and I want that to be my positive Z. So let's first take a little navigation through. So we go positive Z. I want it to go through my Y component. So I go positive. What that then allows it to do is then says, right, Z is now moving upwards. This, as far as setting up your procedure for the robot arm, this is where it's at. This is the tricky bit. Once that's up and running, it's gold. It's working perfectly. So if I click save, click apply, and just for completion, I'm going to do it on the other side as well. So it's quite nice because at least then I get to repeat the procedure that I've done, so you're aware of how to do it. If I come back here, I go to frames, go to edit, and so it's right. I'm just going to rename that actually, call it horn. So at least then it's all got the same name. And just going to zoom in. Don't forget, I want the Z to be my positive Y. So where my Z is here, I'm going to say no, I want this primary axis to be in my positive Y. I'm hoping I'm going to hit an issue here where I'm going to have to change my secondary axis as well. Because how this system works is it looks for one primary axis and it says, what is my secondary axis? And then it knows it has a third axis, and that will just be defaulted. So it uses primary and secondary axis as the third axis is automatically defined. So I'm going to click save and just check my allocations. You see the horn in the right spot. Happy days. So we're now in a good stead, good position to get it moving. And I'm going to close that. Well, no, in fact, I'm going to apply it and I'm going to close it. Now we're at a point where you guys can, any of you can choose which way you want to go with it. Both will work, but I'm going to stay with my solid. I'm just going to comment that out. And now what we need to do is think about how this thing works. So I'm just going to bring up the model again. Think about how this works, the interface with it. Really, we'd need to start building this even more in depth. I mean, I'm tempted. That's what I think I'd like to do, is to build this whole thing up just as a worked example. Depending on how much time we get to, and depending on how much time it takes to get to different things, I think we might even do that, because this is thrust bearing. So that bearing actually does an awful lot here, and it allows it to freely flow around its particular axis. But anyway, right. So if we look at how this is interfacing, I'm sure the degree changes between it were plus or minus, I think it was plus or minus 20. I need to pull up my original model to just remind myself exactly what that full angle turn was. But if we look at how it works, we now know that the interface from the servo is straight to the actual horn. So we're going to fix it. We're going to go straight to that horn. So we know that from there, we have a rotate. So I'm going to go joints, and I'm going to go revolute joint. So bring in the revolute joint, and flip that round. This now becomes that rotation, as we know. Now, because on this original horn down here, we had an axis around Z, it means that it will continuously rotate around. So just bring that down a little bit, and then we've got a way for it. So I'm just going to put that over there. Again, I'm going to upload this model because so that's why I'm leaving it there. So at least then you can see the two alternates of what I was producing. Right. So we're now gonna have the next interface cross. I've gone with solid. I'm thinking that perhaps I should do solid and surface or alternate between the two, but I'll go solid because I think I'm going to end up using the same techniques, because you should realize that here now we're actually using a similar procedure to actually bring these things together. We've got the edges of particular geometry. So I'm going to go onto here and then just call this horn. I'm going to double click in. Now we've got the weight of the servo. We need to be specific as to the horns themselves, exactly how much they weigh. What I'll do is I'll cheat a little bit on this and I'll speed up out the process for this. So I'm going to go servo discs. So I should call, my God, some of these things I've named it on here is just rubbish. Right, so just going to bring that right back to there and then delete and then apply F5. So at least then now we've got the disk. Now the disk with this again has a messed up R value sets. I say messed up, it's not actually that bad, but it is not exactly what we were doing. What we were doing is using the edge of the servo, so we're going to presume it sits inside of the edge in here. So we need to make sure that that's right. Now, when I said I was going to cheat, we need to know the weight. So I'm just going to right click, going to open this. And yes, I think this is coming as Ali. If anybody's wondering why my CAD's really shiny, it's just because it's a Quadro. It's a NVIDIA Quadro. Great for CAD, shite for gaming. Believe me, tried it. I'm just going to use a nylon. I think there's a nylon actually in SolidWorks for me to use. It'll just give me a quick idea of what type of weight we're looking at. Tell you what, it's going to be just me messing around. So I have no idea if there's actually a nylon in there, but what I will do is I'm just going to quickly Google density of nylon. Because I know that they are nylon. Now, according to this, the density of nylon is 1.15 grams per centimeter cubed. So we need to drop this down. We're going to go grams per centimeter cubed, and we go 1.15. The values that we put into this is vital, just to make sure that we're getting true, honest values, true results is vital that we know. So do an update. We've got everything calculated there. So I'm going to go frames, and here I need to be relatively clear. Well, I'm just trying to get the results. If it's true on, well, yeah. Anyway, so that's what I'm just using for this. So I'm going to go to frames, and what I'm going to do is attach to the point of where we were interfacing with. Now, this is where it can turn into a big mix-up. So if I just double-click back into my servo horn, and then just check exactly which edge I used on my horn. And I think did I use the internal? I did use the internal. So at least it lets me know now that when I attach to the next one onto the horn itself, I need to use the internal. I was just double checking just in case. So we'll go servo. These names, they don't have to be particular. They're just to help you to remind yourself when you're navigating through this. So if I click save and then click, if I click selected and then click save. Now this, the only reason, I mean, I know some of you now will be looking, that's wrong, but the only reason I'm doing this is I just wanted to show a few people this in particular. So if I close this, I click apply, then okay. Now the only reason like I said, the only reason I'm doing this is because this has been a common problem so far. There's been I've seen a few like this. So I'm just gonna hit save first, and it's just because if anything's gonna go wrong, it could crash. So I'm gonna go servo test 645. Oh yeah, forgot. And then we go save. And hit run. Right. That's been a real common one. I've had a lot of students saying, what have I done wrong? So you kind of look at that and it will run. Now, just for some giggles, just to see if this runs like we think it's going to run, which it clearly is, I'm just going to run a state, and I'll run a velocity, and we'll actually put it on revs. We need to change this, but let's put it on revs. I'm going to go 2 revs per second. And what it should do is just go a little wrong. So this is totally wrong, and I've seen this time and time again. Actually, in the past few weeks, to be honest. So what went wrong? It was me with my servo connection. If you remember, I forgot to change that axis. Look at the axis there. Z moves here. Now, if you remember how you applied the original axes, this will make your life so much better. So, for example, if you're doing the piston and it's upside down, if you're putting on the crank and it just appears really weird, it's because of these relations. It's because of these relations in particular. You want to try and match each frame behaviors. If you try and match it, what you'll get is a natural build on the model. If you do an opposite of it, you'll get an upside down representation of what that model's doing. So this is pretty much how it's initially functioning. So what I will do is come onto here. And if you remember, we did say that we wanted Z, our positive Z, to actually be moving through the positive Y axis. So I'll go positive Y and then save and then apply. And that then, yes, because it's sitting on R, isn't it there? And that then, it actually moves up here. It looks a bit messed up just because of that relation. So if I now run it again, just to check, what you should be getting now is just that, where this thing is just continuously running. It's not true representation of what we're doing yet, but where this thing is continuously running. So the next bit with this, now I don't know how many people have realized this yet. This is just a straight assembly, so it's constrained to the top of it. What we need to do is actually decide where it's going to be constrained. So I'll come back to my original. interestingly, this horn, the way that we've selected it, will be fine. But this next piece is a little bit more interesting. So if I bring this down, I'm going to call this horn fixing. I'm going to double click in. What I actually want to do is bring that horn fixing in. Now, does anybody know the density for PLA? Because the horn fixing is PLA. It's okay, I'll get it in just a second. So if I go servo horn fixing, click apply, click OK. I'm going to update that. And that is a servo horn fixing. Typical layout, typical how it's all put together. So we now need to attach it in. Density of PLA. Google top search on Google says 1.24. Okay, so come back in here. Go 1.24. Again, I'm going to update. And now, you'll notice I've got many colors coming in now. So I'm just going to make my life a bit easier. I want to actually see this thing, make sure it's connecting correctly. So what I'll do is I'm just going to change that color, and I'll probably just make it something simple like white. That went well. That's better. Forgot to F5 it. So now I've made it white. So then when it interfaces with the servo horn, I can see that it's actually connecting as I want it to. Now, the other thing I want to really decide with here is I'm just going to put servo horn on this frame because this is going to be the point that I'm going to use to connect to it. At this point, if you notice, it's actually picked a strange circular position from God knows where. It's actually been selected because this is a curve this is the curve 35 on this geometry. It's all this is coming from. It's just simply that. So what I'll do is I'm obviously not going to use that curve. I'm probably going to use the internal curve of here. And then I'm going to click save. I'm going to use selected. Right, so we've now hit that big issue again. If you look here, look where that Y is sitting. That is now incorrect. We do still need to have that relation. We still do need to have it keep that theme of X and Y moving in the correct directions. So what I'll do is I'm just going to shift my Z back to my positive Z. So it resets everything. And then I kind of look and go, right, okay, how do I actually want it now? I actually don't want that now. Now, this is great because I was saying what I wanted to be able to do is show you guys the idea of having using that secondary axis. Because what we got to do, if you notice on the frame axis, on the secondary axis, X is already defined. Some of you are probably finding this, so I'm just going to show you this error and just show you that it's not doing it. It's not anything to really panic about, but it's something that's really key within what you're doing. So if I go to along frame axes, what I'll do here is I will actually shift this to my X. As you notice here, I want it to be in that positive X axis. So I'm going to shift it to the positive X axis. And it goes, whoa, 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 what in the hell are you doing? This is this is purely because what it's actually doing now is it's saying you're using a primary axis and a secondary axis on the same axis. That is totally illegal, does not function, and does not work. So what you say is, I want to use these two as my primary axis, but in my secondary, I just want to use Y in this case. So I'm going to shift it to my Y. Then what it says is, oh, okay. And just making sure that I'm still within that orientation. I've still got some relation between it. You look here, and I've now got Z acting upwards. So in my case, I'm trying to keep Z acting upwards continuously. So then I'm going to click save. Oh, let me just check. So you're not really meant to click save. Direction upwards. Yeah. Okay, yeah. And I'm going to click apply. And then okay. Now, just before I forget, I'm going to put that on. R may prove to be a bit of a pain in the backside. So what we'll do is we'll actually remove R completely. So I'm going to F5 on that. And that just stops the tab from being introduced. You'll notice there's pieces on this. I'm simplifying. I'm trying to get rid of them because I don't want them to be a pain. I don't want them to be in the way. And to be honest, I do, as silly as the jokes that we've had, I do like it to be a tidy box. And it's just purely because it should be well presented. If it's not well presented, it's a bit crappy. Let's face it. It's not the best. So the other thing that we need to do now is I'm going to drop R off here as well. If I drop R off, if I drop R away from the actual geometry itself, what I can now do is spin it up. And what I want to do is I'm going to add a new frame into it. And I'm going to go servo fixing. Horn fixing, I should say. Horn. So I've gone horn fixing. And I'm going to go based on geometry. Remember, we use the outside edge. So I'll go outside edge. I'm going to use selected. Using the same methodology that we were discussing earlier. I need Z to be pointing upwards. So what I'll do is go Z. I'm going to push into the Y component. And click save. Now we're going to see if this works. This might come out a little bit odd because you'll notice that the frames I was using then, they were slightly different. And when you have slightly different frames, it can be a bit of a pain. So first things first, let's connect these up. And I'm just going to hit. Looking good, looking good. So that's good. That's good. Now the thing is, now what this is essentially suggesting, is these two parts are one piece, and this is actually not true. What you'll find now is the system will add these two together to fuse it as to one, but they both have their own densities to give representation. Now, because we're talking about these being screwed down, fixed in particular ways, they're not glued together, they're screwed together. Really, you're talking more of a weldment behavior of where the two relations are quite broken. They still have their moments of inertia that inflict against each other. So they relate to each other, but they are not fixed together like glued in this way. So I'm going to use a joint method, which we've not really had to use, and it's not the most complicated one in the world. I'm going to get onto this, and we'll probably find that it's been taken away because everything else seems to be taken away. Right, here. So we have a weld joint. The weld joint refers to the two components still remaining within their moments of inertia, but they are temporarily connected. This is a similar sort of thing like bond on ANSYS. When you have your bonded components, similar sort of behavior. So what we'll do is drag and drop a weld. And I'm going to fuse these two together. Well, not fuse. I'm going to constrain these two together. Now, what we can actually do with this is we can extract constraint forces. So as we're applying force to it, we can actually look at what type of force is passing through the relation of the two. And then what I'm able to do is I can take some of them forces, put it straight back into ANSYS, straight back into whatever weapon of choice you were using, and it allows me so much more. So that's why I put that there. So I'll just click OK. We're not actually going to do anything with it, but it's sexy that I have that option to be able to do something like that. So let me just come back. And have you ever been in a position like this? You kind of go, oh, I don't know. Oh, I can't get in there. Oh, I just can't get in there. Oh, that's, oh, hell. What you can do, if you are interested, I'm gonna actually put this into 4 pieces. So I should point out that with each frame set, I can sort of come here, I can spin it to there, and a little bit there, like that. If I run it, I can track it from each initial step, make sure it's doing something. Now, at the minute, these degrees are far from outside, far from what I actually wanted. So, I know, I could not agree more, Corona. You know, I was going to call you Nick, but clearly I was wrong. But now, with them jokes, I clearly, definitely know who you are. Right, so someone's messaging me. Oh, it's a shame. I actually don't care. Right, so we've now got the full thing built. I suggest what we do is we tag on to the end of the fixture, and then we start to look at applying our restrictive forces onto it. I am going to put on the 8.79 newtons straight onto it. It is too much at first, really. We've got so much rotation going on. We've got the thrust bearing going on that it's probably far from that. But what I can really do is make sure that I'm testing this servo to a ridiculous level and making sure it's going to deliver like I want it to. Or at the same time, if I know that weight and I don't know what servo I need, this is going to help me decide which servo I need. It makes a really, really good bit of kit for that reason. So if anybody is aware of the Bill and Ted project I've been doing, the Python project as I named it, I have been working on Bene, which is more of a humanoid structured system, which I will show you by the end of this session. Right, and I'll explain to you exactly what was going wrong with it. So we got the PLA, we're actually working. Now, I'm going to drop down. I'm going to add this selection on here. Now, the way that this is intended to interface is around this particular area. I think, really, how this is working, I just need to apply it in. So I'll go, so we'll just call this force. So what I'll do is I'll apply it onto this edging. Arguably, could you apply it to the face? You could. Let's put it to the face. I'll just put it onto the face. This is not about a typical geometric representation. This is more about how we're applying it. Now, don't get this mixed up. What I'm going to do is leave it in its original orientation. This will allow me to look at the geometry I'm using, and it'll allow me to be clear about which way the force should be going, because this is where it gets really, really confusing. If I flip this round, it will go a little bit mental, because what I mean is if I flip this round and we try to attach force onto it, it's going to get confusing, because you'll look and go, well, which way is it meant to be going? How is it meant to be going? And we'll be getting results where we go, that's not right, and it's because it won't be right. So I'll leave it in this state. So I know with this, what I'll actually do is, I mean, arguably, which way should it go? I mean, if I go on here, go back to the original geometry, come back on, oh no, I'll just update that. Yeah. One thing that's irritating me with SolidWorks is just, well, I don't know, everything really. Yeah, you can. Yeah, Corona. You could. If I come back, if you are on 2019B, in fact, let's do that. So then we're consistent all the way through. So if I go, I'll come onto that edge and we'll select it. This is just a restriction onto it. So it's going to allow us to have that point there. And all we've got to think is, are we applying force in X or are we applying force in Y? And for me, it's going to be Y. Why? Well, I've got to laugh. No one else will. Because it's revolving around this way. There's going to be a restriction coming down. This is what I meant. It's actually not going to be 8.57 newtons. I should have really calculated that out just to get it nice and in. But if I put in the maximum, what it will actually mean is if it's the maximum that's acting on it, if any of these components really die, can this thing still support? So if I come back out and then click apply, let me just check them. So with the forces, R's not in function, so I'm not bothered. Right. Now, I know some of you have been already applying these forces. Some of you, I do know you were kind of confused as to how to do this. And this is one of the reasons that I'm doing it. So again, this example is really heavily themed on the robot arm. I do intend to do other examples. So what I'm going to do is going to pick out a really, really basic suspension system, and we're going to build that. It's just to try and get people started, because I know that this assignment is difficult. And as far as I understand, a good thing about what's happening now with the coronavirus is we've got some flexibility that we can do stuff here. We can do an awful lot with it. I won't elaborate too much, but yeah, there's yeah, thanks, Corona. We couldn't have done it without you. You do know everybody can see these comments, don't you, Corona? Yeah, just checking. See, I had one yesterday was putting comments on it. It's going, what do you mean everybody can see it? Right, where? Oh, yes, I was going on a big old... So I'm coming on to... Just out of curiosity, has anybody landed in the classroom? I don't know if anybody saw in the email. The classroom is still booked. You can use that classroom. We've been advised not to, but it is still there. So you can use it if you need to. But this is the final day. In fact, when it comes to the end of this, I just want to discuss with you all about that, just so you're all aware. Right, so now I've put on a transform sensor. All this will actually do now is, what am I doing? I'm not putting a transform sensor on. It's me being daft. Sorry about that. That's me trying to track its position. I don't want to know its position. So I'm going to go to forces. Yeah, it's all right. Not everybody knew, but the room is there. You can use it. But we've just been advised to stay away from each other because, you know, now we just get to be proper British. Oh, no. Get rid of you. Right, so I've come on to forces and transforms. Forces and torque, sorry. And external force and torque. So bring that in. And we did use this, if you remember, on the floor linkage bar. What I'll do is connect these up and then double click. This is where we need to get it right as to what we're applying to it. Remember, we're going to go in the Y. Before I just apply that, I just want to bring in the servo horn. And if I go to my frames and transforms, we're discussing the idea of that on my Y. That is initially where that restriction is going to come from. It's going to be coming from there. Really, to take it to the next phase for testing, we need to actually build the whole thing up. So we attach it to there, and we're going to go OK, and then we're going to apply. So you'll notice now it comes in. Now, that triangle lets me know it's looking for one particular value to come in. You can just type this in, by the way, but I'm naturally going through each step because I want everybody to know the architecture, the library where you find these things from. But you can just type it in. But what I'll do is go to Utilities and then go Simulink to PowerStream Converter. Don't forget the PowerStream refers to 3 components. It's all 3 components. It's a Cartesian behavior. But what what Simulink will do is it'll bring it in as 1, and then the PowerStream will bring in 2 extra zeros to in that Cartesian, so it knows what it's being brought in as. So I'm going to drag and drop a PowerStream converter, and then I'm going to connect. Whoops. Like that. Now we know from the value I gave you that our initial value is going to be in newtons. It's just a direct restriction. So there's no dynamics from this particular thing that's moving. So we know that it's just the newtons. Now, the next thing is controlling this. This is what I meant about this is more like the assignment for the robot arm. We need to think about controlling this. So what I'll do is first, I'm not going to mess around with just putting fixed values onto it. I'm going to go straight to the signal builder. Now, I think it's hard to get your head around this at first, and it's just to really spell this out in black and white. The signal builder is simply a particular value you're feeding into the system, and then you're converting that to something. So in this case, I'm going to be bringing in my 8.2, just double check. My 8.53, sorry, my 8.53 newtons. So that's what I'm going to be feeding that in as. However, we do have restrictions on this servo. Now, the thing is, what we really need to look at is we want this thing to sweep. So it's going to sweep over a particular time. It cannot move like a rocket. Somebody showed me a robot arm this week, and it was moving so quick. It was actually moving, I think, about 10 times quicker than a bullet. So we need to be sensible about how this thing responds. That's a good point, Gareth. You could ramp it. That's right. Now, what I'm going to be presuming on this example is that the force that's going to be applied, well, the restriction that's coming on from the, in fact, it's quite nice. I've got the model open. So 2 seconds. The restriction that I'm going to be applying onto this function here. God, I need to fix this. Oh, wow, I've really wrecked it. The restriction I'm going to be putting on is going to be it's going to be effective all the way through. It's never going to stop. So when it comes to that, that's different. But you're right. So what I'll do first is I'll go to Signal Builder. So it's sources. We have Signal Builder here. I'm going to drag and drop that in. Now the beauty is we've now got everything we need. Before I actually attach this in, I'm going to double click into Signal Builder. We know we're going to have a continuous value. So I'm going to click on the above. So if I'll extend this out so you can clearly see it. So you see these 3 here. We can break these down into different types of signals. So you've got your step. Now these steps are interesting. You can turn this to a ramp. But literally, as Gareth's comment was about the ramp rate between it, it's absolutely correct. If we just go a step, in fact, let's put in a step onto the servo moving. We'll see this gigantic step between it. If you're wanting to control position, then you ramp, and that ramp between the two, you can control how quick something will move. So if I was restricted to, I don't know, 2 meters per second, for example, then what I could do is actually examine this. But the trouble is I've only got 1 servo. In the assignment, I think you've got around 6 joints. These all must not exceed 2 meters per second. Anyway, right. So I'm going to add a constant. My constant in this case, and the reason I turn it into this is because I can play around with it. If I wanted to see what would happen if it was loaded all of a sudden, What if somebody came along and did something really stupid, like, I don't know. The trouble is with these heads, when these run, I get people who come up and like put the hand on it. They go, oh, yeah. And it's just weird. Just weird. But they do it. They genuinely do it. Some people will just put their hand on it. And as silly as it sounds, you've got to actually design for around these things. Oh, Corona's typing. It makes me worried when you're typing, Corona. No, I don't think so. No. The heads have never been broken yet. But no, what you're referring, I will actually explain at the end of that what you're referring to there. But it's not that they're broken. They just, the trouble is I don't know who was here. I did have a member of staff, because if Corona is who I think it is, the other day I did have a member of staff in here, and they just stroked the head, and it was just weird. Put the hand on the head, and then, oh, what are you doing? And then when they put the hand on, and then the head just like tilted off into God knows what. And it's like, it's just weird. I'd never seen anything like it. Anyway, yeah. Then Corona, you are the one I'm thinking of. Right, so I'm trying to not dig myself a deep hole here. So what I want to do is have this a continuous value. So we know we're going to be operating to 8.53. So you see how we've got these 10 seconds overview or overlay here. Now this is 10 seconds. So over 10 seconds, we're going to do this testing. You must think in real time. If you drop the arm to move the entire distance it's going to move in 10 seconds, it's going to be moving relatively quick. I've asked for multiple actions for it to occur. It was just go through the roof. Anyway, so on 0, you see how we've got Y and we have T. So T is 0 to 10. You notice there's no Y here. This is purely because it's constant. But if I go into Y and then go 8.53, it then puts it up to 8.53, and it's just a particular value. It is not, it doesn't know it's going to be newtons until it feeds through the Simulink to power stream converter. That is then, it's attached with a unit, and then it knows what it's doing. So before I even start controlling the servo, just want to make sure that this runs through and that it's happy with that. It's just because it... let me just come back in. Now, this always irritates me. I'm going to rename that. I'll just call this force out. And I'm going to rename this. It does genuinely help. Oh, hang on a second. All right. Yeah, it does genuinely help to rename these. So I'll call this servo control. Again, it's because if any of you have taken on the ARM as an example, you'll know that you start to build these up and it just says signal 1, signal 2, and you go, brilliant. I've no idea what I'm looking at. So I'll connect this one up, and I'll just run this as a test. So I'll just bring back on my test screen and then hit run. If anything goes wrong, right, another thing that's really useful, let's say you're doing particular points in space and you need to make sure it's moving as you want it to, it's in the right spot like you want it to. Don't hit just run. See the right side here, you've got update diagram. If I left click and update diagram, what it then does is just updates everything that's going on. So then let's run it again. Yeah, it's going all over the place because really all we've said is just react to a particular thing. And all it's doing now is it's just continuous into one space. Basically, it's not right, but the beauty is it's not crashing. So the allocation's fine. We are going to need to take a look at these spikes, make sure it gives us something that we're interested in. So this is good. This is good. I'm just going to rotate that a bit. The reason I want to do that is I'm I'm very conscious about having this presentable. It's really, really anal. That's a good point. Now, when we put the revs in, all the revs will do is they will just continuously deliver. Really, if I go onto a plot now, I can actually see torque that's been delivered as a response. I can actually see what's going on between it. But you're right. You're right. Once the revs are on there, you do get this confliction, and it's a resistance between the two. Now, the rev will operate in clockwise, and the force will operate as a response to it, and it's just purely we will get that in particular there. But because the rev will just keep going round, you'll always get this restriction. But at the minute, that's why it's not quite right. That's why it's missing bits. So, like for example, we still don't have any real damping between it. This damping gives us that uniform behavior, if you will. So let's just add these in, and then we can start to see something a bit more realistic that we can review. So what I'll do is go back into my Revolute joint. And what I'll do with that is I'm going to go actuation. Now, this is where you need to decide what it is that you're looking for. For me, it was about the torque. So we'll do it this way, but for me, it was about the torque. I got involved with this project through one of the robotics staff. 1 second. I got involved with this project through one of the robotics staff. What he actually said is, what he actually said is the university doesn't build robots. We should be building robots, not buying them in like every other university. We should be doing something where we look and go, oh my God, that's amazing. This is custom. This is truly what we make. Now, I won't lie, I get nervous when I'm selecting any type of particular component. I need to make sure if this runs, it doesn't have a meltdown and it doesn't have any initial problems. And there's not anything that I'm missing. So I ran this through again and again because I wanted to be sure as I was doing it, it was going to be right. So that's why I was going to spend this money on these servos, and I kept thinking, God, I hope they're right. So I ran it through this way, and I was more than right. So yeah, just saying, mic drop, Dickinson out. So I can provide an input from a torque if I know it. Now, if you found a motor, you could provide that torque input and see if it will actually drive it that way. If you're unsure of a motor and you need to select it, I'm going to automatically compute it. And you see on motion here, it says automatically computed because it means that the revs that have been applied, it will actually calculate out the velocities and accelerations and positions based on whatever value it is that you're putting in from the state targets. That's useless for me. So what I'm going to do is say provided input. Before we move on, I'm going to go to state and I'm going to drop my velocity. I'm just going to apply that before anything. I don't want to have any issues there, but I've now got provided input and mechanically computed. So automatically computed, mechanically computed. I swear to God, even though I'll wake up in the morning. So let me just bring that down. And now bring that down a little bit more to there. Across to there. Oh, I do like my tidy boxes. Anyway, so I'm going to right click. Now, I don't know if you saw this. I kept doing this, and somebody said to me, how did you do that? So let's say we've got a particular component. You go, I can't be bothered to go to the library, which sounds weird. Can't be bothered to go to the library. I just want to copy. So if you right click and just drag, it will automatically copy. I've got used to doing that so much that I was doing this on Microsoft Visio. I was making a diagram the other day and it wouldn't work and I just got really annoyed. And it's just because I got used to doing it so much. It's an awesome, awesome function. I love it. You see now, I don't even like them oh, hell. Sorry, I've just got to fix that. Oh, this is a mess. More awkwardly, this has all been recorded. Oh, yeah. Oh. Look at that. Oh, that's awful. Right, I will get to it in a minute. Let me just. It's all right. Anyway, so in the conversion, now don't forget on this. Yeah. Now that's what I'm doing now, Damien. It's a good point. Now, because you've got constant values, you've got things like that. What I'm doing here is I'm using the signal builder because I can choose how much I want to do. Now, if you remember, I said before, it was around 20 degrees plus or minus. I'm going to operate to 20 degrees plus or minus for how this thing is going to move. And that's what I actually want to test against. I want to see these particular spikes to make sure I'm on the right. Now, because you're right, the only other option is a constant value. Constant values, if you're doing something like the robot arm, it will just spin. It'll look like a helicopter trying to take off. So what I do here in my PS converter here, what I need to do first is say what am I going to operate in. I'm obviously operating in degrees. Now, forgive me if anybody's quite experienced with motors and they got used to motors and they know how motors work. The only reason I want to show you this is because it's really useful to know. A motor, because of how it's functioned, will have second order behavioral things. So you'll get, if you imagine your PID controller, where you'll get the overshoot and then you'll get settle point, any type of second order system will behave in the same preferential behavior, if you will. And what I want to do is make sure that my motor behaviors is comparable to what I've done formerly. So under the input filter, provided signal, I'm going to drop down. Now this is golden, golden if you're doing anything like this. Sorry, I get very enthusiastic about this, clearly. So what I'll do is go filter inputs by derivative calculated. Now it says the particular behavior that's coming in, is it first order? Now, if it was first order, this would obviously only be referring to two initial components. If you think of it as first order behavior, if you think of a first order system, you'll know that in a first order system, you actually don't have a mass. You'd have, for example, it'd be like a spring damper example. So a spring damper in that type of example would be like a door shutting. But this isn't that. In this case, this is a second order filter behavior. Now, the relative input time constants, what it will essentially do is it will use, it actually, interestingly, it actually starts with Runge Cutter, and it will look at overshoots between it based on the mass, based on everything else that's there, based on any damping that we're going to apply to it, and then it will give you an order of a response. And you would be blown away to see how accurate this is. In fact, because this is all now going to go online, I might actually do this. We could do this for real because I genuinely do have this servo and we can have a comparative. Anyway, my real focus now, without going on a huge tangent, is to make sure that everybody's happy with the assignment and how to really navigate themselves around this. So I'm going to click apply and then OK. Now we said we were going to go 20 degrees positive, 20 degrees negative. Now I'm going to do this over 10 seconds. So I'm going to go to this particular point, left click on here. So you see on here, we're on 0 all the way through. What I'm actually going to do is move the point. So I'm going to go to Y, put that onto 20. Don't forget, we're feeding a value in, nothing more. And now, just to really come back onto what Gareth was saying about the ramping process, you look over this point, we've got 1 second, 2 second, 3 second, 4 second. We can actually see how fast it's moving based on that. So I like to come back to that because it was a very accurate and a good point to make. What I'll do is shift up my second point. I'm going to go 20. Don't get me wrong. We can make changes to this. And what we'll do is we'll go for an aggressive reaction. So over that was 4 seconds. So to 8 seconds, what we're going to do is try and double that. We're going to try and take this to 8 seconds. And then what we're going to do is move to -20. Because don't forget, this is about a positional state. So it will start from 0, move to 20. Then it's going to move its way back. And then we've got 2 states of speeds. So then I'll go to T. I'm going to change that to 8. And then from there, I'm going to go to -20. And then from here, let's be over 2 seconds. We now know that that really needs to sit at 0 seconds. Because if you look, 2 points between the two. And what we'll then do is we'll try and return the servo to the same position. So it then starts at 0, moves to 20 degrees, then rapidly comes back, moves to -20 degrees of the 0. And what's interesting with this is we can find out what's the initial position of 0 for this particular thing. Then after 8 seconds, it will then return itself in 20 degrees back to 0. So it will move across, right across, and then back to its home position. Before we just run this through, is there any questions on this? Is there anything that you're unsure on? Like I said, I'm recording this. You can reflect on this, and I've got Teams, and everything's all up and running, so you can always just get in touch with me. And while we're still here, I am in EIC 214 all day long, so please drop in if there's any issues. I'm not finishing yet, by the way. I'm just saying that I'll be here. Right, so let's bring this back. Let's close this. In fact, I'll leave that open for the minute. Yeah, go on, Corona. Yep. Yeah, exactly. Exactly. And that's why I thought this servo was a cracking example, because everybody's seen the servo in function, and then when you actually see this thing move and you kind of think it genuinely is just moving to a degree that you tell it to, it's almost digestible a bit better. So I intend to do stuff over the next few weeks right through like this, and we're just going to keep doing stuff like this. Obviously, attendance monitoring is through the floor now. It's total crap. So I'll be doing stuff like this, and I am also open to any suggestions if anybody wants me to do any particular type. What I thought I might do, perhaps next week, what I thought I might do is we might do KTM 525 build, and I'll take you through that. It is a brutal build, but it's rocking. Awesome. Absolutely rocking. And I'd like to get you to a position where you come away and go, why has he got a PhD? You know what I mean? Because it's so easy to do. Right, so I'm going to bring this back, rock that back in, and let's just make sure everything's running. So again, I think for this, I was just trying to show you the split screen here. So I'm going to actually go back to single screen. And if we're right, you look at where that servo's sitting. So we now know where 0 is, because don't forget, it's zeroing itself. If I run, please. I know, right? That's what I was just thinking. So it's running. So we got it. We got that. We've got that. And the one thing to keep in mind is if you are starting an initial position, I mean, with this, all we were doing is testing the performance of the servo to make sure that it's particularly useful for this job that we're aiming at, which I can't believe how badly all this has fallen in bits. It's just because I've not touched a lot of it in a while. If you're aiming it for doing a particular job, then obviously we'd need to fix these. We'd need to know what that degree would be and then know it a bit more. What I'm probably going to do is I'm going to take Bill home. And if I take Bill home, we could do some live stuff online, doing proper data acquisition on it and get some stuff from it. Again, I'm probably going to do that as a bit of an extra thing just because it's not really your assignment. So it's just because it's an awesome thing to do. Right, so we've now got to start, we've started to get some output from it. Now what I want is first, I'm going to presume that the damping behavior on it is going to be the same as what we've used before, which is 0.001. So I'm going to go 0.0, whoops, 0.001. Is it 00? 00? I think it's 001. And then I'm going to apply that. This just starts to give me a representation of this thing rotating, and I'm starting to get some sort of result with it. So the next thing that I want to know is I actually want to know how much it takes to move this bad boy. Because we've got the true values, we've got the true representation, we can actually start to really see what's going on. So I'm going to go to sensing. Now we're applying actuation onto this. We're applying directly onto this. We can either go constraint force, torque, or total torque. Total torque will take everything that's been brought in and also everything that's coming out straight out of it. Because the actuator will just come straight from it. In fact, let's look at the actuation torque, because really what I want from this is to know that it's moving. I'm not sure if it's going to give me anything yet, but what we'll do is we'll come from that. And I'm just going to bring this up. I just want a bit more space, tidy boxes, you know. And now what I'll do is I need a power stream to Simulink converter. Again, if anybody wants to type it in, that's fine. I'm just going to navigate myself to it. So I'm going power stream to Simulink converter, bring that in. And yeah, so run onto there, and we've got that connection. Really, it's Newton meters, but I'm going to go scope. It's scope. Everybody knows where scope is, so for that, I'm going to type. I was tempted to try and spell it wrong, just so someone would jump on my back instantly. So I'm going to double click in. Come on, you swine. Now, not exactly what I was looking for. We do have these restrictions on here. Not exactly what I was looking for. What I really need is the total. So I'm going to remove that. I need full spikes on this. I need to really know exactly what's going on. So I'm going to go sensing. I'm going to remove that. Then I'm going to go total torque. This will extract everything out of what's coming. Now, the thing is, when it comes out, you end up with total primary and secondary torques that are coming out, which tend to look something like that. Now, this doesn't really tell us anything. Not really clear on anything at all. Could do with some units. So we'll go Newton meter. Right, so now when it comes out, this you can kind of look and go, what in the hell am I looking at? So let's bring this back. And what I'm going to use is what's called a demu. Or for anybody who's English and knows how words work, which rich coming from me, is demux. So DMU. I always forget where the demu is. Number of inputs, number of outputs, sorry, 3, because we know that there's 3 values coming through that we don't know. I'm just going to drag this out a little more. I'm going to put this onto here. Then what I'm going to do is attach onto here. I do appreciate that we're going to have to come to a close at some point, just because I'm not technically allowed. Well, I'm not supposed to take up everybody's time as much as awesome Simulink it is. But what I'm going to do is attach here, and attach here. What the Dimu will do is it will see 3 particular values that are coming through, and it will turn them into separate pieces. So if I run it again, watch this. Boom. I know, right? Feeling very cocky right now, just saying. I know, right? That's exactly what I was thinking. See how we got these curves? See, now, it's interesting that Gareth pointed out about ramping, right? You look at the distance across. We've got a steady flow between it. Interestingly, there are no spikes on this. Now, the real spikes on this that actually occur here. These spikes can move towards where you'll have shock on any type of torque. Now, because of how simple this is, we've got a nice overview on it. It is a very straightforward torques that are coming out on it. What we really need to know is, will the actual recommendation of the motor be something workable? Now, the original recommendation of this motor is... let's have a look. Torques out on this is 7.7 kilograms centimeter. So 7.7 kilograms centimeter. Interestingly, we can probably actually put that in as a unit. Let's try putting it as a unit. To be honest, that's one thing I've never tried. So we're going to go kilograms. Let's see. Let's try kilograms centimeter. Yeah, it's probably not going to do that. So we'll go back to Newton meters. What I'll do is I'm just going to have a quick look at these servos. Let's just see what their maximum output is. These are a HG645, a high torque servo. So let's have a look. So, there is one in particular I'll give you. Now, these are quoted as being high torque. So let me just double check. So kilograms. Right, so these are quoted to be at. Kilograms percent at 9.6. Now, one guy here is claiming that they've had. Wow. Copyright. They're claiming that they had just at around. Just under, well, it's actually 0.4 Newton meters. Oh, really? Right. So, apologies, Corona. Come back on. If you go on to just as a check, does your layout look like this? Corona. Yeah, I thought it might do. Right. Double click into your scope. And what I did is I just added layout. I separated it into 3. It's just so I could put them, because what you'll still get is you'll get the same thing in the scope if it's just one. So you've actually not done anything. So then if you run it, you'll get these 3 steps. So it apparently, these servos will actually operate to 0.04 Newton meters. That seems awfully high in comparison to what I've physically seen. I've actually seen about 3 in a case, because sometimes it can be quite heavy on it. But the good news is as a selection process, it will work. I'm happy with that. It's going to give me what I want. It's going to allow me to do exactly what I want. My maximum outs here, the spikes, according to this, are practically nothing. But there's not much joints there. All I've done is attach a constant value. Now, I know that we're running out of time, which is really irritating. What I wanted to do is, I'm going to actually, let's say I'm going to plot this, and I want to actually put this into a report, which I did actually write for this project, which is really nerdy. I actually brought out my initial total torque value. So I want these values to come out, so I've got something to report with. I don't use the scope. The scope is absolute poo. So what I'm going to do is come on here, and I'm going to put it out to workspace. So if I go workspace, give it a minute. I'm just going to search through workspace. See where you got sim out here. Sim out is mint. So if I drag that in, right, drag that in, and I'm just going to call this a servo joint, servo torque. Oh. So I'm going to servo torque. Yes, you could, Damien. Yes, you could. The data inspector will allow you to extract direct stuff from it as well. What I'd recommend though is you use that and you use the initial stuff that comes out of it. But if I attach this to my output torque here, then run it again, what it allows me to do is take these values away from this simulation and actually put it into something where I can actually take the out. So this, for example, this is my out. And if I go my servo torques, and let's go plot here. Now what I've got is something a bit more sophisticated. I can now bring in, so for example, on my tools, I can now do data statistics on between it. I can look at max and mins, medians, standard deviation of what's going on actually on this curve. What I can do as well is, if this was a noisy signal, I can use filtering. I can play around with these values, and there's a lot more I can do with it by doing it this way. And when you output this, so if I was to output this, if I just for this example, if I output this onto the desktop as an enhanced meta file, so I'll put it on the desktop. Enhanced meta files are really good for if you wanted to put a document, if you wanted to put a document together and you want a plot to look awesome. So I'll just show you what I mean. So I'll just put it into my plot. And then go. Don't get wrong. You know what I mean. If I click off to that now, click off. What it allows now, I mean, if I change the font size, but as a plot, it says everything I want it to do. And the beauty is as well, from in here, I can change font size. I've got so much more freedom to be able to do it. So I'd always say, use the scope to allow you to analyze the data even more, but don't go crazy of we're just using this scope, because there's an overall presentation tool. It is a bit poor, to be honest. Right, so what we've done is yes, you could. If you want to see more noise on this, I mean, all I've been doing here is, in this particular process, all I've been really doing is just wanting to look at this as a motion. The other thing about this is we didn't really see a spike. Now, these spikes are vital. So if I just come back and then go to my original curve here, and if I go to my signal builder, because this is why I was using signal builder, but if I go to my signal builder, and then if I wanted, I could actually, for argument's sake, let's do a spike straight here. So we go at 0, And then I'm just adding a random one in here, but I'm going 8.3 to copy. And then where my step comes in, I'm going to change my Y value to 8.3. What it now becomes is a point in where it spikes. So if you're having something that wasn't loaded at all and then is introduced, it will spike it. So I'll just quickly remove you, add you in, and we should get some shock reactions. These shock are interesting because what they're actually coming from, you must have seen this before when somebody builds something and it won't move. And then if you just gently tap it, it starts moving and it runs fine. It's because it needs to overcome that initial momentum. In fact, there's a few things I can show you on this design that went horribly wrong for me. Now you look there. Now, initially on this, it doesn't really tell us much, but if I go to my zoom in tool, I'm just going to zoom in amongst this particular point. Then what I'm going to do is I'm going to come down between here to here. See these overshoots here. Now, this overshoot here is coming purely on that. It's truly fascinating because when you see it react and you see that these things are behaving, you'll see it spike. These spikes can be monstrous. But these are things just to keep in mind. Right, so I know that this procedure and doing these classes is really weird. I mean, I know that some of you guys will be sat there thinking this is a little bit weird. It is weird. I should first just reiterate of that the university is genuinely doing this to try and protect you and protect all your families as well. I mean, for us, even me, yes, even though I'm older, for us, it's not too much of a concern, but it's all for those who are a lot more elderly, and that's why we're doing this. That's why the whole country is doing this. So I do really share in your frustration. Moving forwards, we are going to be I'm going to keep doing this, but the beauty is I'm going to try and make this as a benefit as much as possible. So I'm going to try and make something good out of something really bad. So I'll be doing these again and again. I'm going to try and promote a bit more discussion because the beauty is with this, we can do some crazy stuff. We can throw this into, we can see how well this performs on Mars. We can look at these types of things and see what types of reactions we're going to get. This I thought was a nice example as to selecting mortars, and which is a typical example of how I personally did it for when I was doing for the Python project for building Bill and Ted. What I will do is I think I might build a bit more of this. The next session, I think tomorrow's session, what I'll perhaps do is focus on build of the engine. For anybody who's taken on the challenge of the engine, it looks dead simple, it looks dead straightforward, and in many ways it is. If you've hit that roadblock, that is the cylinder axis, now you know why it's on the assignment, because it does give a bit of a miss. A lot of people just think, oh, it's just the engine, just nail it. And then when you actually get into it, you go, oh, no. The rubber arm is based around what we're doing here. So I am going to try and keep building these up. I hope you found this a bit of a benefit this morning. I hope that it's helped out with any misunderstandings or anything like that. What I'm going to do is I have been recording, so I will upload this for anybody who missed it and anybody who wants to run through this again. I will also upload the model. Again, what I'll call it is CAD Session 1 with an upload. That does not surprise me. That's working, Damien. I won't lie. You were pretty close to it the other day. I won't line. You are probably one of the first in a long time to actually get this running straight so quickly. Quite impressed. But it's one of them things. Now, just before we close all this down, Has anybody got any comments or anybody any concerns apart from Corona? I you know, as far as the virus goes, it's a nightmare. It's a nightmare for all of us. So I am going to admit to some very awkward things now. So now, just taking you back to this example, remember when I was talking to you about the overall design of this? What went wrong? Wow, what went wrong is an understatement. So I say it's not too much of an understatement. The other day, there was a member of staff who was in here and genuinely stroking this head. Genuinely stroking the head. Never seen anything like it. It just left me feeling really awkward. Everybody in the room was kind of like, what are you doing? Anyway, right, I don't want to dig anybody deeper with that, but that was genuinely what was going on. Right, so come back to this. So I started running this example test, and I realized that the head was 25% too big. I've made it like that. To be honest, I've never made a skull before, so it was a new experience for me. And then these push rods. The way that this works is, can I actually open these push rods? Let me just see. I can open you up an eye. So if we open up an eye for a second, I'll show you the initial thing. If anybody wants to chip in on this, by the way, you're welcome to. I mean, I know that you're all very busy as it is, but that's particular how it works. So all it will do is if I push it and pull it, it will rotate around its axis and allow it to look around the room. Now, what I actually found with it is when somebody's in the line of sight of this machine, what it will do is I have in lack of better words, a boundary, a line of sight. And what it will try and do is always keep you in line of sight. But you can step into a position. Now, because of these servos incrementing the way that they do a degree. So a degree, so what it means is if it gets to a particular point, the eye will actually start to resonate. And it's not because of the servo, it's not because of the code, it's because I designed it that way. So this proved to be a big problem. I've still kept up with the design for this and using multibody. Yes, I did. Yes, I can't actually say that on recording because that is. I genuinely did. Yeah, I did. And let's have a look. Yeah, you know, this, Damien, is a comment. What's the best methods for measuring stuff in accuracy? Now, this has been feedback to Dassault. I mean, not Dassault, to MATLAB for years. Why can we not measure anything? We can't seem to measure anything. If you know the way that something moves and you're putting in that value, happy days. But as far as measuring something about geometry, I just can't find anything that's there to do it. And that's going to be part of my mission over this week, by the way. Somebody told me that a novice has introduced a measuring tool on the file exchange. So I don't know if that exists yet. So I'll need to get back to you on that. But at present, I'd say use a CAD system. Right. So if I take you to my actual new build. The issue is the design, the eyes weren't right. It was quite difficult, quite tricky. So what I did is I started to redesign a new one. Now, this is one that I nicknamed Benny. I thought I'd name them all after comedians. I know, right? And this one now... Oh, it takes forever. This one uses more of biomimicry. So basically, I've just based it on how eyes genuinely move. And don't get me wrong, it does look a bit freaky. So this is now sat in my home at the minute, and my wife is not the biggest fan. Weird, right? But this is obviously based more along the lines of the human skull. I've modeled all this here. I've modeled the internal. I've actually tried to make it look similar to it, so they all look related. The teeth are based on the same teeth, but they're more of human size now. And this now uses, let me just hide you. This now uses biomimicry as an option rather than anything else. My God, this is like really slowing down. And what we got in here is that these eyes will feed into here. There's cables that feed through there, and now it's a cable driven, and it uses a muscle design of like the human eye to just get a bit more accuracy as it moves. So each one is tied, and you get a draw, and everything does it pretty much that way. So that is where I'm still using multi-body to try and design servos that I need and how it works. Anyway, right, so back to actually to it. Again, I hope you found it a benefit. I am here all day. If there are any particular questions, please come and find me. If once we shut down this evening, this does prove to be a little bit out, then what I would suggest is get in touch with me through LinkedIn, and not LinkedIn, through Teams, and we'll take it from there. The other thing that I need to just stress to you is I heard a horror rumor today of that they're going to close the buildings down at 5 o'clock this evening. That's what I was told, but it was just by somebody who was in the gym. So you never know. I'm going to try and find out, but I'm planning to not get kicked out by 5 o'clock, but we'll see. I am in EIC 214 if you need anything. And thanks a lot. And I'll upload this and speak to you all soon.